miles west of the lake, positive velocities take her east, and negative velocities take her west. So here's the graph that we have been given. What is the cyclist's approximate position at t equals 1 hour? That's A. And then B, when is the cyclist farthest from the lake? How far from the lake is the cyclist at this time? So in order to determine this, we're going to be looking at the given graph, and we're going to see how we can use this graph to find the area of the graph at different intervals in order to find how far the cyclist has traveled after 1 hour and what that means in order to answer the question. So the best way to do this is going to be using a Riemann sum. In this case, since the instructions haven't specified which Riemann sum we should be using, I will be using a right-hand Riemann sum because that's what I prefer. And in order to get the most accurate measurement, we're going to be using about 6 rectangles. The more rectangles, the better the estimate, but since I don't have time to do infinite rectangles, we are going to do just 6 today, and also just to keep it simple in order to talk about how to do this problem. So we're going to start by marking the graph with the right-hand Riemann sum that we're going to be using. So each of these sections here is going to be 1/6 of an hour. So we're going to call this the first one t equals 1/6, the next one here t equals 2/6, and so on. So let's start with t equals 1/6, the right-hand Riemann sum here, and we can go ahead and mark that. Okay, then going to t equals 2/6, you can see it's going to be flat because it doesn't extend. I'm going to actually go ahead and use color that you might be able to see a little bit more. There we go. Okay, and then above the x-axis, we're going to be doing the same thing. Oops, sorry about that. It's going to be up to where the graph is, all the way through, and then same thing at each interval. And this one's going to be flat again. Okay, so now that we have the graph marked as it needs to be, we can go ahead and start writing out the equation that we're going to be using to answer the question. So let's go ahead. Okay, so I started off by writing the equation for the Riemann sum here at the top. So we know that the width of each of these rectangles is going to be 1/6 of an hour. So I went ahead and wrote here, as you can see here, 1/6, which is the width, times v of 1/6, which is going to be the height. So now that you can see that, you can go ahead and move on. So I did the same thing throughout. So they're all going to have a width of 1/6. So I went ahead and wrote 1 plus 1/6 times v of 2/6 plus 1/6 times v of 3/6 plus 1/6 times v of 4/6 plus 1/6 times v of 5/6, and finally plus 1/6 times v of 6/6, or 1. 1 was easier. But so that's going to be how we're going to be setting up the equation. And now that we've done that, we can go ahead and write in the height of each of these rectangles to get our estimate. So you can say, let's see, sorry, so right hand, oh, sorry about that. Okay, right hand equals 1/6 times, now we need the height of 1/6. We can see here that it's going to be about -10. So we can say -10 plus 1/6 times v of 2/6. We can see here that that's going to be 0 because it is just on the x-axis. So we can write 0 plus 1/6 times v 3/6. So that we can see here is going to be 20. Plus 1/6 times no, not V, excuse me, V of 5, 6, no, 4, 6, sorry about that, which is going to be 30 plus 1/6 times V of 5, 6, which is 25 approximately, plus 1/6 times t equals, so the height of t equals 1, which is once again 0 because it is on the x-axis. So now that we have that set up, we can go ahead and do our calculation, which I'm going to write next to the question now. So you can put that in the calculator if you want to. But I'm just going to go ahead and write what the numbers are when you do that. So when you see that the right hand 6 equals negative 1.66 plus 0. It's going to be plus 3.33 plus 5 plus 4.16 plus 0. And when you add all that up, you're going to get that equals 10.83, which is because the negative 1.66 has to be subtracted, and so ultimately you're going to get 10.83. Okay, so this 10.3 is going to be the change basically that's happening between t equals 0 and t equals 1, but it asks us, so what is the position at t equals 1 hour? So in order to find this, we need to look back to the problem and see that the cycle starts initially 5 miles west of the lake. So that's going to be important for calculating the position, because the position is not just going to be t equals 10.83. So let's start off by saying that, I'll go ahead and do this in a different color to make it a little different. Okay, so let's say that since we know that the S of 0 equals negative 5, and we know that the change between 0 and 1 is going to equal 10.830, and that's going to be movement really to the east. And so, in order to calculate the position at t equals hour, we can say that the S of 1 equals the S of 0 plus the change between t equals 0 and t equals 1. And when you put that all together, you're going to see that it's going to be 10.83 minus 5. It's 5 because the cycle starts initially 5 miles west of the lake, and you're going to be seeing that the answer is going to be 5.83. So, and then we need to find our units, and the units are going to be miles because it says miles per hour, and then times hours equals miles. So that's going to be our unit that we're going to be using. So let's move on now to the next question. And the next part of the question, it says, when is the cyclist farthest away from the lake? How far away from the lake is the cyclist at the time? So now we need to look back to the graph, and we need to think of a few things. First, we know that the cyclist is initially 5 miles west of the lake, and that when they begin moving between t equals 0 and t equals 1, they don't start going east right away. They continue going west, because we know that because the movement that is negative takes you to the west, and there is a negative section of the graph from t equals 0 to t equals 1/3 hour, or t equals 2/6 an hour, whichever way you'd like to say. But what's important is that this part of the graph here is negative. So that means that the cyclist is continuing to go west at this time, which means that this area is going to go ahead and show us that the cyclist is continuing west at this point, which means, just to give you something to keep track of here, that means that her movement west is going to be the -5 that she started initially with, plus more negative movement or more westward movement, which is going to be -1.66. So that's going to equal -6.66, or that's her movement to the west. And so then we know we can take our answer that we got earlier, 5.83. We know that's her movement to the east because that was when we already accounted for her initial position, as well as the fact that she did not start going east right away. We already subtracted the -1.66 from our answer back when we were doing the round sum. So because we know that, we can say, okay, so the cyclist moved, counting her initial position and her movements between t equals 0 and t equals 1/3 hour. That's going to equal -6.66, or 6.66 miles to the west. West, if that helps. Or 5.83 miles to the east. So I think it's pretty clear here. So the cyclist is furthest from the lake at t equals 1/3 hour. Because the cyclist's movement to the east between t equals 0 and t equals 1 is 10.83. However, the cyclist's initial position, like I said, is 5 miles west of the lake, so the cyclist only travels 5.83 miles east of the lake in 1 hour. Keeping this in mind, we know that the cyclist did not start traveling to the east at t equals 0. The cyclist continues traveling west until t equals 1/3 hours because v is below the x-axis, meaning that it's going to become -6.66 or 6.66 miles to the west. This means the cyclist traveled 6.66 miles west of the lake, but they only ever traveled 5.83 miles east of the lake. Since 6.66 is greater than 5.83, t equals 1/3 hours, or 6.66 miles west of the lake, is the furthest the cyclist ever travels from the lake. So we can show here that 6.66 miles, I'll go ahead and rewrite it, is the furthest distance from the lake. And that that's 6.6 miles is how far they were, and t equals 1/3 is when they are furthest apart. This is when they're farthest away. It's a little cramped, but I think you can still read it. You can see here how this is going to work. It's just to give you another visual. So we've successfully answered all of the questions that are here. We answered these questions on this page and this page, and so I hope you have learned a little bit about how to use the right-hand real sum to answer this question, and thank you for watching.